Okay, we're back. The last video got cut off after the third example, but hopefully that was enough to give you a good idea of how to find specific solutions to indefinite integrals. Now, we're going to get into examples 4 and 5, but before we do that, let's get into this pesky question of why we care. Well, there's a variety of reasons to care about getting a specific solution versus a general solution. So let's go back to, or if you think back to the Khan Academy videos where he took the derivative of a bunch of very similar functions. So let's say we took the derivative with respect to x of 2x plus 5, and the derivative with respect to x of 2x plus 3, and the derivative with respect to x of 2x plus 100. Well, all of these are 2. So if you're going to do the inverse operation, integral of 2 with respect to x, it's got to be 2x plus something, and we don't know what the something is. It could be any of the c could be any of these things, and without more information, you don't know which one. Could be these three, could be something entirely different. All we know is that it's a constant. There's no x terms or there's no variable in there. So that's one way to look at this. If you take derivatives, you lose constants, and therefore when you take integrals, you have to put the constant back. And if you want to know exactly which constant, that's where your second known quantity comes in. The other way to think about it is to go back to the fundamental idea of what a derivative is, and look at two functions that are the same except for the fact that one of them is shifted upwards from the other. So if we draw two parabolas, upside down parabolas, so we got this one, and then let's draw an orange one, and we'll assume that they are identical except for the fact that one of them is an upward shift from the other. The orange one is an upward shift of the green one. Well, remember that derivatives are the slopes of tangents. So if we were to draw some nice thin little tangent lines here, we find that at that point the derivative is 0 on the orange function, and at this point the derivative is 0 on the green function. Let's do the same thing at x equals whatever the heck this value is. So over here we get about a 45-degree angle, and we get about the same thing at this point. And in fact, if these two functions really are just vertical shifts of each other, then they will give us the same a tangent with the same slope at every single value of x that we put in there. And that means that their derivatives are the same. But clearly the functions themselves are different. And so in order to distinguish whether you want this function or something else, you have to have one known point on the function. Let's do that in blue. If we know that this point is part of our function, in other words, if this blue dot here is our x0 and y0, then that tells us that the green function is the function we want as opposed to the orange function or any other up-down shift. Similarly, if the black point here is our x0 and y0, then we know that the orange function is the one that we actually want as our specific solution. So that's two ways to think about why we want specific solutions as opposed to general solutions. The last one gets back to physics. And so thinking about this in terms of the most simple branch of physics, which is kinematics, we know that the derivative with respect to time of x is velocity. The derivative with respect to time of velocity is acceleration. So derivative of position is velocity, derivative of velocity is acceleration. Let's just focus on this one. If I were to give you velocity as a function of time, oh, by the way, there's a flip side to this logic, which is that the integral of velocity with respect to time is position. But if I just give you a velocity and a time, then you cannot calculate an actual position. So if I were to tell you that your velocity is 3 meters per second, and you've been moving at this velocity for 30 seconds, then you cannot tell me where on the planet or where in the universe you are. You would also need to have a starting point. Oh, by the way, with this information, you can tell how far you are from where you started. But if you want an absolute position, then you would also need one known point and a corresponding time. One known position and one corresponding time for that position. The easiest one to measure is usually your starting position, your initial position. So when time is equal to 0, x is equal to 0. So if you start at the origin, then after 30 seconds moving at 3 meters per second, you can say x of 30 would therefore be 90 meters. But notice, without this piece of information, without this one known time and corresponding position, in other words, the known x0 and y0, your integral cannot give you a single value for a single value of your dependent variable for a single value of your independent variable. Alright, we'll cover the next two solutions in the next video, reason being that this camera seems to like to cut out at around 15 minutes and we're already 6 minutes in.